In my lecture, I will give two different topics. One is on application of eddy current testing to inspection of structural component. And second one is risk-based inspection that is included of this in the title of this seminar. But this time I introduce risk-based inspection very quickly, very briefly. So in the previous lecture, Professor Gail Sebald give a very nice introduction of a fundamental aspect of electromagnetic non-destructive testing. So in my lecture, we focus on the application of eddy current testing. That is one of representative electromagnetic testing. And as an application, I focus on the detection of fatigue crack or stress corrosion crack in metal structure. For this technique, I think that this is matured, well developed. And another topic is on the inspection of CFRP. This is an ongoing project, and we should develop this technique in future. And the second topic is risk-based inspection, as I told you. So this again, what you see here is a principle of eddy current testing. So target of eddy current testing is a conductive material. And using eddy current testing, we can detect or evaluate cracks in conductive material. This is due to the geometrical singularity of conductive material. And also, we can evaluate material property, material degradation by eddy current testing. But here, we focus on crack detection that is applied in industry now. So here, I want to introduce a flexible multi-coil eddy current sensor. So this is a photo of a flexible multi-coil eddy current sensor. So you can see a lot of element coil aligned on the flexible substrate. It's similar to a phased array that was introduced by Professor Fiat. But objective of this array are a little bit different from ultrasonic phased array sensor. And this sensor can adapt a curved surface of curved radius of 20 millimeter without any wire breaking. So we can apply this sensor to the weld part like this. And this is a alignment of coil of multi-coil eddy current probe. So a fundamental element is a transmitter receiver type probe, type sensor. So this is exciter and pickup. And this alignment is sensitive to crack like this. So in order to detect a crack for this direction and perpendicular to this direction, so in this multi-coil probe has this alignment consisting of 32 coil. So for this scan pattern, transmitter is located here, and the receiver is located here. And in total, 32 channel is included in this pattern. And these unit can detect clock oriented this direction. And for this pattern, transmitter and receiver align this way. And it consists of 16 elements. And if we move this probe this way, so we can get a region, the signal of this region by one-dimensional motion. So we can get sensing data very effectively. This is the advantage of this probe. And this is an example of application. So this is a target plate, stainless steel, and at the center, fatigue clock is embedded. And this is a eddy current signal, two-dimensional eddy current signal. So you can see here indication of eddy current signal. So we prepare the clock signal, template of clock signal in advance. And using a template matching technique, we can identify the location of fatigue clock. After identifying the location, we clock shape reconstruction is done. So you can see here, this is a result of clock shape reconstruction. So this is a clock shape, and this inverse analysis estimate length 1.18 millimeter length of clock, fatigue clock, and for the depth 1.6 millimeter. And after the fractography, true length we found through both length and depth. This inverse analysis give a good answer. And for stress corrosion cracking, so this is a specimen, and in the center part, stress corrosion cracking is lying. And in the same way, we identify the stress corrosion cracking on the surface. And for stress corrosion cracking, so as you know from the lecture by Professor Nicola Mari yesterday, the surface morphology is very complicated. And the template matching answer the crack shape as a set of a small crack. But anyway, this result can be a good result. Can be good compared to the surface observation. Then we applied this sensor to a round-robin test that is organized by a program of inspection of nickel alloy component, but organized by U.S. Nuclear Regulatory Commission. In the framework of this program, round-robin tests were carried out, and many NDT group in the world join. And this is one of the round robin test sample. This is a dissimilar metal weld specimen for and this is a safe end. This part is a safe end made of stainless steel, and this is a nozzle made of low alloy steel. And these two components are welded by alloy 600. And in inner surface of this nozzle, stress corrosion cracking specimen are embedded in this piping. And this is a result of inspection by our sensor. And this is one example of original data obtained by a multi-coil array sensor. So as you can see here, data is very noisy. But after filtering, we can identify the crack, stress corrosion crack. And this is a comparison between the detected crack by our sensor, and the red one is the answer. So you can see that this crack, this sensor can detect a stress corrosion crack even in the actual configuration in nuclear power station. So now you can see that eddy current testing is very well developed to apply industry. So as for another target, I will introduce application of eddy current testing for CFRP component, especially hydrogen tank made of CFRP. So CFRP, as you know, this is one of composite, and this is made of carbon fiber and resin. And the structure is very complicated. But thanks to this composition, it has a very good advantage, such as high strength or lightweight. But due to this complicated structure, it's very difficult to carry out non-destructive testing. And non-destructive testing technique for CFRP is not well established. So we should develop in future. And what you see here now is representative defects in CFRP. So defects in CFRP is categorized into two types. So defect of resin origin and a defect of fiber origin. And looking at the fiber origin defect, it includes fiber breaking, misalignment, and the fiber content. So since carbon fiber is conductive, so detection of these fiber origin defect, eddy current can work. As for the defect of resin origin, it includes delamination or resin cracking or uncured resin or inclusion of foreign material. So this is a applicability of existing NDE technique to CFRP. So as I mentioned, eddy current eddy current testing, target is a conductive material. So it is good for fiber defects. And looking at the ultrasonic testing, so it is very good technique for detection of resin defect. So in looking at this table, I think that ultrasonic testing and eddy current testing complement each other. And the combination of UT and eddy current testing, I think that it will give a good inspection for CFRP. Anyway, here I want to introduce some results of eddy. I want to introduce some application of eddy current testing for fiber defects. So here, for you to understand the fundamental signal of eddy current testing, so I introduce the eddy current signal for very simple specimen. So this is a uniform configuration orienting. So fiber is oriented in 0 degree, and this shows a stacking sequence. And the probe using here is a transmitter receiver type probe. So pickup coil is located here. This is a differential, and exciting coil is here. So for this alignment, fiber this fiber orientation is sensitive for this sensor. Anyway, after scanning this specimen, we can get eddy current spatial distribution of eddy current signal for UD ply CFRP. And as you can see here, there are many striped patterns. So here, in order to analyze more, so we extract this line, eddy current data on this line. So as you can see, there is a periodical pattern here. And after FFT spectrum, so peak at 170 meter inverse are found. And this corresponds to a pattern of a 5-millimeter interval. And this corresponds to a fiber bundle pattern. So eddy current testing can detect fiber bundle information in unidirectional prepreg. So then we apply eddy current testing for detection of macroscopic misalignment layer. So this is a specimen with a misaligned layer. So basically, this is a cross-ply stacking specimen. And on the third and fifth and seventh layer, there is a misaligned layer inserted. Here, angle of misalignment is 5 degree. And so this is a specimen ID. So looking at the results of eddy current signal, for specimen with a misalignment layer on 7th layer. This is original signal. So you can see that there is no, almost a pattern has almost 0 degree. And you can see the misalignment layer. So in order to pick up this misalignment data information, we apply 2D FFT filtering. So we filter out 0 degree component and a 90 degree component of cross-ply configuration. Then, as you can see here, misalignment information appear. So in order to read angle of misalignment data, so we apply radon transformation analysis. So for each angle, we get the projection data. Then we can get a projection for each angle, projection angle. And if the projection angle is agreed with fiber direction, so we can projected data include a pattern, periodical pattern data like this. But if the angle are different from the fiber orientation, the waveform are monotonous. So in order to parameterize this complicated structure, we estimate tangential slope, summation of tangential slope. Then at the angle of fiber direction, this parameter alpha is maximized. In that way, we can identify, we can estimate fiber orientation. And this is a result of estimation of a fiber misalignment angle. So for each specimen, you can see the peak at the 5 degree. So as you can see here, so eddy current testing is very effective technique to detect misalignment data. Finally, I want to introduce some of results for application of this technique to inspection of a high pressure hydrogen tank for fuel cell vehicle. So this is a real onboard hydrogen tank for FCV. And we cut this tank by water jet machining. And we did inspection using eddy current testing inner surface. And this is an experimental system, and the probe used here is same one as before. Okay, so here, and also we introduce a drilled hole in a surface to see if eddy current testing can detect fiber breaking. So this drilled hole simulate fiber breaking. So, and as I mentioned before, this probe has a directivity. So this alignment, for this alignment, sensor is very sensitive. to this direction. And this, for this alignment, it is sensitive to this direction. And if we align this way, and after the two-dimensional scan, we can get the two-dimensional two-dimensional eddy current signal like this. And this is the eddy current. This is a drill hole indication, and this pattern correspond to a fiber bundle of a hydrogen tank. And if we change directivity, so another pattern appear. So for this data, we obtain the innermost layer. And for this pattern, due to the change difference of winding, we can obtain a second orientation of fiber orientation of second layer. And also, in addition, we apply radon transform analysis. And here we can read angle of a fiber angle of a winding direction of fiber bundle for innermost layer. And also we can identify the angle of fiber bundle in second layer. So I think that we think that eddy current testing is very effective method to evaluate fiber information in CFRP component. Okay, so this is a topic for future direction of eddy current application. Then I want to move next topics. This is related to risk-based inspection. So as I told yesterday, in the framework of risk-based maintenance, we decide the priority of maintenance work of component in a very huge plant. For this purpose, we evaluate risk of each component in consisting plant. And this is a risk diagram consisting of probability and consequence. And both parameter, due to the both parameter, we can estimate the risk in this diagram. Okay. And if some component, if the risk of some component lie here, it means that the risk of component is very high. So we should assign a lot of maintenance work for this component to decrease to decrease the risk of this component. This it can be achieved by decreasing the probability of failure or decreasing to decrease the consequence of failure. And as yesterday, Professor Nicola Murray mentioned, there is a trade-off for maintenance activity. So if we do a lot of maintenance work, we can decrease the probability of failure, and we can avoid accident. But it requires a lot of cost. But if decrease the maintenance work, maybe the probability of failure increase. So there may be a optimal point. But anyway, in order to, we need to evaluate both probability and consequence. But here we focus on assessment of probability. Usually, probability of failure is assessed by applicable damage mechanism and inspection technique. So, applicable damage mechanism. Yesterday, you enjoyed a lecture by Professor Nicola Mali and Professor Danset Silvan. They they gave a lecture on damage mechanism. And according to this damage mechanism, we can predict behavior of material consisting component. And also, we have a lot of lecture on inspection technique. And by inspection, we can, there is a possibility that we can find the defects before the failure. Then we can decrease the probability. Anyway, in order to estimate probability, we should consider both the reliability of damage mechanism and also a reliability of inspection technique. That is important. And on the other hand, consequence. So if we look at a chemical plant, concern is a leakage of flammable outcome or toxic outcome. So we should evaluate leakage rate of this material to evaluate consequence area. And also we should evaluate financial aspect. For example, environmental cost, and also a cost of loss of production due to the termination, shutdown of the plant. Due to this two factors, we can evaluate a consequence of failure. So there is a standard for risk inspection proposed by American Petroleum Institute, API. And the API proposed a standard API 581 in the first time in the world. And today, I want to introduce a fundamental idea of of evaluating probability. So in this standard, assessment of probability is based on damage factor, considering the damage mechanism and the inspection technique. And looking at this standard, you can see the table for the damage factor. That depend on the number of inspection and the number of effectiveness of number of inspection and the inspection effectiveness. And also, this table is prepared for prepared depending on the reliability of the damage mechanism. So I will explain how the factor is decided in this standard. So in order to determine the damage factor, Bayes' theorem is applied. Some of you know Bayes' theorem very well because this is very well known and apply to many statistical data analysis. But anyway, so in Bayes' theorem, we can get the answer, the probability when we, okay, if let's consider the situation where we know the results and we want to know the cause of results. So this theorem can give an answer, the probability that if some event results A was caused by condition B from the conditional probability. And the equation is expressed like this. So here, this is a diagram of this situation. Okay, and now we know the results, event A, and the possible cause. There is a 3 condition. Let's say condition 1, condition 2, condition 3. And now we want to know the probability that cause event A. Probability of condition 1 that cause event A. In this case, this new denominator of this equation correspond to this region surrounded by blue line, and a numerator correspond to this region. In that way, we can calculate the probability that condition 1 is a cause of a resulting event A. So let's think about example. For example, if you have a cancer test and you got positive results, you want to know this test is really reliable or not. So this example is about a health checkup problem. So let's consider disease A that affects 40 persons per 10,000 in a country. Let's imagine this disease is something like a serious one, like cancer. Then, if a person suffering from a disease A undergo a medical checkup, and there is a 80% chance of a positive result. So 80%, for 80%, this test give a correct answer. But also, if a healthy person undergo medical checkup B, there is a 90% chance of a negative result. It means that for a healthy person, 90% correct answer can have a correct answer. It means that this test, reliability of this test is good enough. So if you so now question is what is the probability that someone has a disease A if he or she tests positive by test B? So this diagram shows the situation here. And this axis represents a real condition. So this boundary, this is a boundary for between the normal health people and the people suffering from disease A. So since 0.4% people suffer from disease A, so this region, people suffer from disease A, and these are region for normal health people. And this axis indicate the test results. So positive results or negative results. So for people suffering from disease A, these are the positive and these are the negative. So this is this situation is a false. And looking at the normal health people, if they got a positive, this is a false result. And this region corresponds to true result. Okay, and now we consider the situation that someone got a positive result, and we want to know the probability that this person is really positive or not. Okay. So this is an expression of expression by Bayesian theorem, and based on this diagram, so denominator is this region. Okay, and this region is a region for false, and this is a true situation, and this probability is calculated this, and the answer is 0.03. So probability is 3%. So this person got results of positive, but and the reliability of test is 90% or 80% high enough. But results is 3%. Maybe this is much smaller than you expected. But this is due to that amount of ratio of normal health people is quite large. Due to this fact, the probability is small. But if we look at this result in other view, without test, we know that just the possibility of 0.%, we have a possibility to have a disease A. But by test, confidence increased from 0.4% to 3%. So that effect of a test. Then this we think apply this situation to inspection in the plant. Let's think about inspection of pipe wall thinning. So this is a pipe, and we measure the pipe wall thickness by ultrasonic testing probe. That is explained by Professor Pia yesterday. So by ultrasonic testing, we can get the thickness, pipe wall thickness, and if we repeat the measurement, we can get the trend of thickness change like this. Then we can estimate a corrosion rate. So now let's think about the situation. Corrosion, we can know that the corrosion rate is 1 millimeter per year by corrosion model. And in this situation, we apply non-destructive testing, and we got the answer that we got the measurement data that corrosion rate is 1 millimeter per year. In this case, how is the probability distribution of actual corrosion rate? This answer can be obtained by applying Bayes' theorem in the same way before this health checks. Okay, so in order to answer this question, at first we determine the reliability of model for corrosion. Okay, so let's say here now a corrosion model predict that the corrosion rate is 1 millimeter per year. Okay, and based on the reliability of model, we set the probability of a correct answer assigned 0.5. But actually, as you can see here, if the actual corrosion rate is less than estimated rate of 1 millimeter per year, in this case, it is acceptable, we think. So as far as answer is conservative, we accept. It's a very rough model. And if the model give a wrong result, let's say actual corrosion rate is less than sorry, this is more than twice the estimated rate. So in this case, model is not conservative. This probability we set at 0.3, and 4 times we set 0.2. In this way, we define the probability density function very roughly. And also, based on the reliability of inspection, we define the PDF of a probability of non-destructive testing. So if when a non-destructive testing measure 1 millimeter per year, in this situation, actual corrosion rate, if the actual corrosion rate is less than a measured rate of 1 millimeter per year, in this case, our probability is 0.7. Let's see. Okay. Then, if the actual corrosion rate is less than twice of the measured rate, in this case, we assign 20%, and 4 times 0.1%, 0.1. So probability density function become like this. In that way, we define the reliability of non-destructive testing. In this situation, we apply Bayesian theorem. And here, this is in this table, we pick up all possible cases. There is a 3 case for a actual rate is 1 millimeter per year. This is and less than 2 millimeter per year, or 4 millimeter per year. And for measured rate, there is 3 cases, less than 1 millimeter less than 2 millimeter, and less than 4 millimeter. Since we got the results of 1 millimeter per year by inspection, so this is a result, obtained result. And in this situation, by Bayesian theorem, we want to know the possibility that the inspection measure correctly. In this case, we can estimate this possibility this way. Okay, denominator correspond this 3 case, and the numerator correspond this case. Okay, in this case, before the inspection, the possibility is 0.5. So without the inspection, the possibility of 1 millimeter per year, it is just 0.5. But after inspection, the possibility increase from 0.5 to 0.814 by the confirmation of inspection. Okay, so in this way, we can estimate other situation. And before the inspection, we have a prior distribution based on the corrosion model. And by inspection, we got a posterior distribution with high reliability. And also, we can repeat inspection more than 2. In this case, a prior distribution is set to the results of first inspection. Okay, so this is same as this one. And after the second inspection, we can estimate this probability density function this way. So confidence can be updated by multiple inspection. You can see confidence is increased from 0.1 to 0.94. Okay, so in that way, we can estimate confidence by inspection. But the question is, in standard, how we set the reliability of data, experimental data or model. In API 581, the reliability of data used for the prediction is defined this way. So it has 3 categories: low reliability, middle reliability, and high reliability. So if you have field data that is very similar to the situation you have, in this case, we can define this data is high. And in this case, correct possibility of a correct answer is 0.8. But if the data is based on laboratory data or some other data, in this case, we set middle. And if the data is from the, for example, some other literature, in this case, we categorize this data into low. In this case, the probability of correct prediction is 0.5. In that way, we can determine the prior distribution. Then, how to define the effective effectiveness of inspection method. In the standard 581, effectiveness of each inspection method is determined, is categorized into 5 categories: highly, usually, fairly, poorly, and ineffectiveness. And for each inspection, expert panel determine the effectiveness of this inspection. For example, if the effectiveness of inspection is high, in this case, the probability of correct answer is 0.9. It's very high. But in the case of ineffective inspection, the distribution is flat or 1/3. So almost nothing. So this is what you see here is a confidence update by various inspection based on low reliability data. So without inspection, we can know just the probability. We can know the correct corrosion rate at the possibility of 0.5, very low. But if you apply poor inspection technology, a little bit confidence is increased. And by repeating, for example, after 5 times, confidence increased to 0.8. But if you use highly reliable inspection data, in that case, just one inspection give update the confidence very effectively. So you can looking at this confidence update, you can select inspection technique and also determine the number of inspection, maybe depending on the possible maintenance resources can be allocated. Okay, so behind the table, behind this table, this kind of calculation, there is this kind of calculation. And basically, engineer for maintenance look at this table. For example, if the current thinning rate is for example 0.16, if you don't apply inspection, the damage factor is 19. But if you apply a poor inspection technique, it is improved by 70. But if you apply highly reliable inspection, it can be improved very effectively. But even if in the case of poor inspection technique, if you repeat inspection, you can get a very good damage factor. So in that way, engineer or maintenance work in the plant can determine the number of inspection and the number of and type of inspection based on this table in order to get sufficient damage factor. So in that way, we can discuss the decrease of probability of failure by discussing the inspection technique and the damage mechanism model. So anyway, this is the outline of how to assess the inspection to get the risk in the standard. And okay, so I do hope you understand that based on damage model, reliable damage model, and a reliable inspection technique, we can decrease probability of failure and decrease the risk. Okay, so that's all my, this is the end of my talk.